the goals and world model and stuff, right? Now, there's sort of an obvious way of doing this, which like anybody who's ever seen any category theory will start out with right away. You've got your like chemical equations, and you've got whatever equations are describing your like agentic model, so like phase and stuff. Like utility. We're going to say like this is a low-level model, this is a high-level model. There's going to be some sort of coarse graining or other type of function connecting those two. And what we're going to hope for is like we can do some sort of predictions on both levels, right? Like maybe we predict how the system is going to evolve, or maybe we predict something in some other aspect of the behavior of this thing. What we're hoping is that we can sort of do the prediction at the low level, then translate it to the high level, or we can just translate to the high level from the get-go and then do the prediction at the high level, and we should get the same answer both ways, right? It's like the categories standard Munich square type idea of how abstraction works.
Wait, sorry, what was the display arrows?
Some sort of prediction. I'm being very hand wavy here. I'm not committing to like what sort of predictions we're trying to make here. It doesn't really matter. When I like go try this, you know, like 5-6 years ago, I go try this thing, code this up for like a simple system. Turns out these functions are just like massively underdetermined, right? There's just like a crap ton of ways that you can view this this bacterium as encoding some sort of goal-directed behavior, and most of them are not really the things that we think of when we think of this bacteria encoding some goal-directed behavior. So like the point here is that apparently our intuitions are relying on a whole bunch of constraints that are just like not captured by the most obvious thing, right? Somehow, if we want to accurately capture these things that biologists are intuitively using in their heads when they talk about organisms having goals or modeling the world around them, is that like they're able to make predictions about what the organisms do by using these concepts in their head. This apparently is relying on significantly more structure than just this simplest possible thing. So like, what's the rest of it? And that's basically going to be the topic of this talk. Make sense?
Can you give a counterexample on something that fits the structure?
No.
What'd you say?
In general, you all are welcome to ask questions, and sometimes I'm going to say no.
What'd she ask though?
I'm not repeating it.
Okay.
We're just plowing on ahead. All right, so high-level structure here. I'm going to give like sort of the high-level categories things I'm going to be talking about. Then I'm going to draw some pictures in each of them, like the sort of mental pictures that I have in my head when thinking about each of these things. And then we're going to dive into like places where we have theorems, places where we have conjectures, sort of what the actual mathematical structure is. Okay. So first category of things is going to be natural abstraction. And in scare quotes, I'm going to say this is in the territory. So already at this point, we are going to be talking about like framing things in terms of agents, but we're going to be trying to bring in agents in order to establish things that are kind of agentic. Then the next chunk of things is going to be about representations and embedding. And this category is in the mind, whereby in the mind, I mean like in the physical stuff that is operating as, right, like in your brain. After that, we're going to cross the divide between like stuff that can be basically just epistemic and stuff that's not just basically epistemic. We're going to start talking about agency, and in particular, different levels of agency. And then finally, we're going to talk about multi-agent. I'll note that while I have drawn these in a square, there's no particular analogy between those two things and those two things, so I don't need too much. Now, some pictures. When I talk about natural abstraction, what am I talking about? Let's think about good old Alice and Bob. Now, both of these agents have like stuff in their head, right? They've got models of the world and all that jazz. For purposes of this talk, I'm usually going to picture world models as like big causal nets. That's not very realistic, but it's going to be good for gesturing at things. And in a few places, I'll try to explain what a somewhat more realistic model would look like. So in Alice's head, we're picturing some sort of big causal model. In Bob's head, we're picturing some sort of potentially different big causal model. And both of these are like their models. Then out in the territory, we've got a thing, like a tree, for instance. And we're imagining that, like, inside of their heads, Alice and Bob both are doing some sort of abstraction for purposes of communication, for purposes of efficient queries, whatever. Probably you can picture like some sort of coarse graining within this model. Bob's doing some sort of other coarse graining in his model. And what we're hoping here is that both of these two agents coarse grain out some part of their model, which basically corresponds to that tree. Why would they both do that? Because, for whatever reason, the world around them kind of naturally factors in this way prediction purposes. Like lots of different predictions that you can make efficiently if you're sort of bundling a bunch of information together as the tree. And this is like a good way to predict stuff. So this, where the in the territory part comes in, is insofar as the tree is sort of a natural thing to coarse grain out for multiple different agents, like insofar as it doesn't really depend which agent is doing this, you end up with a whatever. You end up with the concept of tree essentially being determined by the territory. Like because it doesn't matter which agent is doing this, because the tree is sort of natural across lots of different agents, in that particular sense, it's a thing that is sort of determined by the territory. Whereas different territories, like Mars, for instance, this tree would probably not be such a natural concept for modeling Mars. Other trees. Yes.
You want to replace it on
That would be lovely. Thank you. All right, so that's picture number one, thing to have in your head while we're talking about this. Picture number two, also under natural abstraction. Thank you. Picture number two. Once again, I'm going to draw things as a big causal graph, even though you don't necessarily need to think of it that way. The important point here is we're in a world that has like space and time, and stuff is distributed throughout space and time. So that means we can think about information propagating through space and time, right? All right. In case of a causal graph, you can picture information propagating through Markov blankets. This gives rise to the telephone theorem. This is an analogy to the game of telephone you may have played in kindergarten at some point, where like you get a bunch of kids in a row and someone like whispers a phrase in the first person's ear, and then they turn around and try to whisper it in the next person's ear, and so on and so forth. And it's hilarious because like you get to the end and the last person has heard some phrase which is totally garbled and doesn't sound at all like the first person's phrase, right? This is the game of telephone. The idea of the telephone theorem is very roughly any information that's not basically perfectly conserved as it propagates is going to be completely lost. So there's this sort of duality between like when you're thinking about information sort of propagating out to a distance, it sort of has to go through deterministic constraints or approximately deterministic constraints. And this, if you went to like Sam's talk on condensation, for instance, or if you've seen any of our stuff on natural latents, this was sort of like the early argument that convinced me that the things we need to be looking for purposes of like natural abstractions are mostly deterministic constraints between like stuff far apart in the environment. Okay, that's picture number 2. Picture number 3 is not a picture, it's a marker. Let's go with this marker. This marker, as you may have noticed, is, to a pretty good approximation, a rigid body object. Interesting thing about rigid body objects, they have a geometry to them which stays roughly the same over time. Crazy concept, I know, right? Thinking about this in terms of the telephone theorem style picture, you've got a sort of latent geometry. This is the information that is basically perfectly conserved for a long time. On the other hand, this rigid body object also has a position and orientation in space, and I can back out that position and orientation in space by looking at any little piece of the marker. Like if I just look at the cap, and I see the cap is here, it's oriented like that, I know basically where the rest of the marker is. If I just look at this end of the marker, I see it's here, it's oriented roughly like that, I know where the rest of the marker is. So there's also this information about position and orientation that's quote unquote propagating spatially. You know, it's not really causally propagating, but it gets like distributed over space. So in the case of a rigid body object, we have sort of these 2 separate variables that are conserved when, so sort of information that's conserved as it propagates in 2 different ways, right? One of them over time, one of them over space. So this is a canonical example of the sort of higher level structure that you can build out of latents that are served in this way. And a central question is going to be, what are the like typical higher level structures that agents Alice and Bob would land on for convergent latents in their models. All right, that's all the topics under natural abstraction. And we are going to like dive a bit more into this. I'm doing the like speed run purposely.
Do you want to add language to that picture?
Not yet. Next up is going to be representations and embedding. When we get to representation, a key concept is that of a lazy role. Okay, so imagine, for instance, a program for calculating a factorial function, right? So in Python, might say something like factorial of n if n 0 return 1 else return n factorial and minus. You can think of this program as a compressed representation of a big circuit, right? If you unroll the big circuit, it would do something like, we have these little boxes, n goes in, it says, is n equal to 0? If so, 1 comes out. If not, something else comes out, which we get by multiplying any different thing. Sorry, other thing. And otherwise, we pass down this stack. So the visual here is this program is a compressed representation of this feed graph where this little box with the dotted line around it, we have a big stack of copies of this. Right? You can think of this, if we frame it differently, as a compressed representation of a world. Like we have a world that consists of this big circuit for computing factorial, right? And if we just stop thinking of this as a function, forget the fact that we usually pass in a thing here and read something out there, you could just think of this as like a whole world with its own like big causal graph. And you can talk about like, well, sometimes in the world, there's like a thing over there, right? There's this little spot in space-time, there's some sort of stuff that takes on a certain value. Then this program would be a compressed representation of that world. And more importantly, it's a lazy representation of that world. So if we're thinking about this like whole quote unquote world, when we query any particular thing in that world, for instance, by calling this program, we're not usually going to compute out the entire infinite graph, right? What we have here is a lazy date structure for representing this. Now, the reason that's important is because in our minds, certainly, and probably in lots of other kinds of minds, a lot of the things we represent are represented lazily in a way basically analogous to this. Which means if you go look in, for instance, a neural network and you're expecting to find like a circuit just fully embedded in there, you're not going to find it, right? You should not expect to find like full-blown circuits in there if things are being represented lazily. You have to be looking for some other structure that's not quite that, right? So a big question in the like representations topic is how do we expect minds to represent essentially pointers to objects in lazily represented world models, right? If I think about, for instance, the genome of that vine over there, in my world model, I certainly have like a pointer to that concept. I can talk about it. You also have a pointer to it, so you know what I'm talking about. But at the same time, none of us know the full sequence of that genome. None of us are like trying to fully compute our prediction of that genome, right? Like the thing in my head is a pointer to it, not a full-blown graphical model around the thing, not a full value. All right, so that's the issue of laziness. Next picture that I want to draw here is one you've probably pictured before if you thought about interp. Picture a neural net, right? Big old net, bunch of like circuits. We've got some branches and stuff. Okay. I don't have any particular kind of neural net in mind. Imagine your favorite. Point is, the embedding problem, what we'd really like to do is go figure out how these, how representations of natural concepts are embedded in that net. Make sense? So that's like putting all of these pieces together. The like ultimate empirical test of whatever theory we come up with is we should be able to find representations, probably lazy, embedded somehow in this net of like that stuff. All right, I'm gonna pause drawing pictures there. Does anyone want to ask questions, which I will then refuse to answer?
Questions.
Go ahead.
How do you identify whether there's a representation?
Great question. I don't know. Anyone else?
Are you trying to develop a science of doing this for particular neural nets or just asking the very general question?
I would definitely like it to apply to more things than just neural nets. Now, we like, part of the point of this would be, or I guess the empirical test of this would be we should be able to take a particular net and like see what the theory predicts and run it on a net, get stuff out that looks like we're expecting. But like the theory itself should be much more general. I should probably the reason why we want theory that's much more general than that is because I don't particularly, even if like LLMs take off in the next 3 years, if they start like doing recursive self-improvement, the second generation of things after LLMs is probably not going to look like a transformer. So I really like my theory to apply to whatever comes after. Yes.
What does any of this have to do with the initial thing of interpreting the bacteria?
Good question. I want you to ask that again after we get to here, and then I will talk about what each of these looks like in the context of the bacteria. All right, on to levels of agents. People talk about agents. Often they have different notions of agency in mind. Humans have various agentic properties that bacteria do not. Bacteria have various agentic properties that thermostats do not. These things I would call different levels of agents, and there are like multiple different levels that are useful and important to think about, usually in order. So I'm going to start with the lowest level. I wouldn't even call an agent. I'm going to call teleology. Now, the picture I have in my head when I think of teleology is I go to the beach and I find a pile of wood. And I notice that this pile of wood happens to assemble into a very nice sphere. that's a rather suspicious property for a pile of wood to have, unless someone like was specifically trying to make it into a sphere, or unless like some natural process somehow made this pile of wood assemble into a sphere, right? So what I would say there is, boy, this pile of wood sure looks like it was optimized to assemble into a sphere. That's that's the thing that I prototypically think of as teleology. You've got a system that looks like it's optimized for something. So the picture here, I'm not going to be able to draw a very good pile of wood, but I guess picture a sphere. That's my mountain. Next level would be a basic agent. And my prototypical mental picture there is going to be the equal. The defining idea of a basic agent is it's going to take different actions or have different outputs or whatever, do different stuff. Do different stuff in response to inputs of some sort. Such that particular outcomes occur.
Outcomes what?
Such that particular outcomes occur. Or another way to put it would be like you can think of it as trying to steer its environment in the sense that it is taking different actions under different conditions in a way that sort of consistently steers towards some cluster of stuff out. Yes.
So you use the word levels. Are you suggesting there's nothing meaningfully between the teleology and the E. coli level?
I'm not necessarily suggesting that there's nothing important between them. I am also not suggesting that there's nothing important orthogonal to them. There is. I am emphasizing these as particularly natural levels to sort of think of in sequence and think of as like parts of a broader thing. So we've got the pile of wood that assembles into a sphere. We've got the bacterium. Then the next level up, last level that I'll think about here is going to be general purpose agency. And this one is an agent that can accomplish a lot of different things. And our prototypical mental picture for this guy is going to be here. In fact, let's get a little bit more specific than that. We're going to say this particular example is Alexander. Alexander has managed to organize multiple conferences, not just one. Therefore, he clearly can do more than one thing. All right. So those are our mental pictures for levels of agency. Thing to emphasize here is that typically we would imagine that these quote unquote higher levels inheriting from the lower levels. So if you have a basic agent, we're usually expecting that it's teleological. Bacteria sure look like they were optimized for something. Similarly, if you have a general purpose agent, it's probably also doing the basic agency thing. If you've got Alexander going around planning a conference, he's probably doing different things in response to different stimuli he gets. He gets an email from someone, has to reply differently depending on what the email says. So the general purpose agent is also doing the basic agency thing. Alexander also sure looks like he's been optimized for something. So it's also doing the teleology thing. So that's why I'm referring to these as levels. What am I optimized? What's my purpose? Well, reproductive fitness would be the obvious guess, but I don't think you have kids. So your face, sorry.
I thought you were.
So you're just saying I'm handsome.
Exactly. Exactly.
So to check, we're lumping together, say, thermostats and E. coli.
Are we lumping together thermostats and E. coli? For current purposes, yes.
Okay.
Then last topic here is going to be multi-agent stuff. In particular, for purposes of all this forming a coherent-ish body of theory, I'm particularly interested in things like subagents and how different agents sort of aggregate into a superagent. I'm less interested for this purpose in things like different agents competing with each other, that sort of thing. Okay. Yes, question.
So something that has been optimized for something looks as though it's like sort of been shaped by the environment in such a way as to like be in quite a particular way. But say like dust on Earth, dust on the moon will be like very, very different. Will it
Okay,
be?
I'm not answering this right now. We'll hopefully get back to it later.
All right.
There is an answer. So multi-agent. What pictures do I want to find? First picture I want in your mind here is a sort of equilibrium picture. So we have a bunch of different agents. And all these different agents face different trade-offs, right? In some cases, they're going to be facing trade-offs between the same things in such a way that they can do better by like equilibrating. So the canonical example here would be like chapter 1 of every economics textbook, right? You've got Alice who lives on one island, Bob who lives on the other island. They can both grow coconuts and bananas. They face different trade-off rates and how many coconuts and bananas they can each grow. And then you would say, well, if these two at current margins have different trade-off rates between number of coconuts and number of bananas they can grow, then assuming neither of them is hitting a zero bound, they can get a Pareto improvement in how many bananas and coconuts they're jointly producing by one of them specializing more in bananas and one of them specializing more in coconuts. The equilibrium picture of this says if these agents are at a Pareto optimum, if they are jointly behaving Pareto optimally, then there should be a trade-off rate which is the same between them. So like maybe 3 coconuts, 2 bananas. Thing I want to emphasize here, usually this is presented in the context of like talking about free trade or whatever. This has nothing to do with trade. If they're both being managed by a dictatorial central power, this still applies. Pareto optimality will still only occur if they have the same trade. So it's sort of natural when we have a bunch of agents to look at them and be like, well, is there a set of them that all have the same trade-off rates? Yes.
So is that a theorem, or like why does it need to stabilize? Why can't it be like ergodic or following some other?
So you would need completely different concepts to even talk about ergodicity. The case in which they would not stabilize is when you have weird convexities, things go off to infinity and stuff.
Okay.
Not going to get into that. Anyway, point here is if you have insofar as this is like assumption 5, a thing you would expect to see a lot is a whole bunch of agents that all face the same trade-off ratios. In like practice, what this looks like is a bunch of agents who are all willing to trade at roughly the same prices. This is a thing that I would typically call a market. Like what defines the market is you've got a bunch of agents that are willing to trade at the same prices, aka they face the same trade-off ratios. When this happens, it's also fairly natural to think of these guys as having aggregated into a super agent in some sense, right? Like the market as a whole is going to also be willing to make trade-offs at this same 3-to-2 ratio with stuff outside of it, whatever that may be. So these guys as a whole are sort of acting as a super agent that like, but that super agent has a somewhat different signature than the component agents. Like even if these component agents are utility maximizers, there's a question of like, well, does this aggregated agent act like a utility maximizer? Under some assumptions, yes. Under some assumptions, no. That's sort of what I think of as the central question in multi-agent systems. Important point here is in order to even talk about all this, we also already needed to bring in a bunch of assumptions from over here. In order for these agents to equilibrate like this, they all need to, for instance, agree on what a banana and a coconut are, right? If they have different notions of banana and coconut, like we don't even have the preconditions for them to be able to trade. We don't have the preconditions for them to be able to outsource work to each other. So all of this like flows through to here once we have some. That's all of the mental pictures. And we are now about halfway through the talk time, which is perfect. Does anybody have questions now? Cool.
So when you say they like all have like the same trade ratio,
Yeah.
it's not like they're not like living on the same island with the same like production ability.
Not
They're like
necessarily, no.
it's like 3 coconuts is worth 2 bananas because you can like arbitrage with your like neighbor or something.
Correct.
Why can't they trade if they have different conceptions of what a banana and coconut are?
Good question. So suppose you and I are in this situation. I think of the world in terms of coconuts and bananas. You think of the world in terms of fruits that are larger than about yay big and fruits that are smaller than about yay big, on which bananas are often kind of ambiguous and coconuts could go in either direction. So I see this situation we're in, and I'm like, man, I'd really like to have Pareto more bananas and coconuts. And I'm trying to trade with you, right? I'm like, I would love to give you 3 bananas for 2 coconuts. And you hand me a collection of objects that are slightly larger than yay big. And I'm like, well, fuck. This wasn't really what I was looking for. I don't think I want to do this trade. Like, how do I even communicate to you what I'm trying to do? And now I'll emphasize that's specifically framing things in terms of trade, but we could just as well frame it in terms of like, there's a dictator telling us what to do in order to get Pareto optimal production. Like if the dictator is trying to get Pareto optimal amounts of bananas and coconuts, and you think in terms of objects that are about this big or smaller versus bigger, what does the dictator even tell you to do, right? Like there's a communication barrier there before he can even get you to do what he wants. Okay, other questions?
To what extent does
You've been singing for a while.
It's a continuation actually of this question.
Yeah.
It slightly confuses me. It's not very typical that people categorize the exchange good in non-matching ways. Probably the most common one are actually quite far developed. So for example, when you build a house or you buy a complicated technical device, that's where there are mismatches. But normally, that's not typically when I say I want a sword. It's pretty clear what I mean. Maybe there will be one question about how big, how heavy. Oh yeah, there you go. Perfect. Perfect. There you go. No misunderstanding. Thank you. Oh, feels good in the hand. Right? Good. Excellent. But it's too warm for the night watch. So my question is a little bit, why is that an important point if it is not typical until the most complex levels?
So the way I would frame this is actually, it's not that this is an unusual problem to face. It's that the things we think of as trade goods are the things where it's easy to standardize. So like products where it's hard to standardize are exactly the products where you don't have these sorts of markets and you end up with like needing much more detailed contracts or like needing sort of lots of one-on-one FaceTime between the producer and the consumer, that sort of thing.
Okay, got it. Thank you.
All right, are there other questions that are not about this last square? Because frankly, it's not the most interesting part. Go ahead.
Detailed question about the definitions of agency, the levels of agency.
All right.
The basic agents, does that imply a goal, an awareness of a preference, like intended agents of sorts?
Awareness is a very loaded term that I'm not going to take a position on.
Okay.
It does turn out to imply a goal, and that's one of the things we're going to talk about in the second half of this talk.
Okay, thank you.
Alexander.
Is your multi-agent work like conceptual?
Now, see, I asked if there were questions not about that.
I know, but I'm using my special privilege. Alex the agent,
Yes.
general purpose agent, and
Yes.
ask, does it involve bargaining? Is that
I don't think of bargaining as like a piece that is central to the theory insofar as this all feels like it holds together in a theory. Like it's sort of
Okay, so that's not your
potentially
So how do you do
a
conflict?
useful piece, but yeah.
How do you formalize conflict?
Like the point of this theory, like I would say this theory is not really meant to talk about conflict. Like it is meant to talk about agents insofar as subagents aggregate into agents. It's meant to talk about that. Conflict is just like a separate topic.
John,
Yes. Oh, one more. Go ahead.
Do the agents above the bacterium have to represent their goals explicitly, or do they
Do the agents above the bacterium? What agents above the bacterium?
general
Hello.
purpose agent
Oh, general purpose agent. Yeah.
above?
That sure is a complicated one. Like, my guess would certainly be yes, but that's the sort of thing where we should really have a theorem for it, and there's a whole lot we have to do before we have a theorem for that. Yes.
You have natural abstraction and representation and embedding as separate topics here.
Yep.
But I don't know, when I think about what makes certain abstractions natural, I sure think about stuff that has to do with, what is like efficient in representation embedding terms. Like, for example, lazy evaluation, that seems like a pretty strong constraint.
Yep.
That like at any particular moment, I want to like minimize the flop and whatever I need to spend to retrieve some answer. I would have naively thought that these kind of constraints sort of shape a lot what's a natural abstraction in the first place. Are you making sort of claim here that you don't think so?
Making that claim. I think the claim I would make there is that insofar as what's natural depends on architectural aspects of the mind, it involves like very weak assumptions on the architectural aspects. But yeah, that's all right. Now, next part of the talk, I want to talk about like these are the pictures in my head when I'm picturing this stuff. What sort of stuff do I expect to be able to say about it? In some places, we have actual theorems. In some places, we have conjectures. In some places, we just have thoughts. So, like, what does that all look like? Starting at the very beginning. So, this part is, like I mentioned earlier, if you went to Sam's condensation talk, this is where condensation goes. If you've read our stuff on natural latents, which is kind of the same thing, also here. So we have theorems already that basically say if there's some sort of latent in a model that satisfies some particular properties, then it's going to be isomorphic to any latent in other agents model that also satisfies those properties. I'm not going to talk about what those properties are. Go read Sam's paper on condensation or our posts on natural latents. Yeah, that's what that is. I will say that, like, conceptually, the key properties line up very nicely with the telephone. Very nicely is overstating. Somewhat nicely with the telephone. Conceptually, the place where you can get this sort of ontological guarantee, this guarantee that like latent over here must match latent over there, is where you have a latent that expresses some sort of deterministic constraint between multiple things in the world, and those things are basically independent, subject to that deterministic constraint. So, canonical example here would be there's air around me, and I can think about the microscopic state of this little chunk of air and the microscopic state of that little chunk of air. And probably there's a sort of handful of macroscopic variables that inform both of those, right? Like they're roughly the same temperature, maybe there's a little bit of a breeze, that sort of thing. Once we control for those handful of macroscopic variables, the microscopic states of these two little chunks of air are going to be pretty good approximation, really ridiculously good approximation, independent, right? That's the sort of situation where like Sam's assumptions are our assumptions bind, and you're going to get this sort of ontological stability. You can also, the marker also tells a similar story. We talked about like it's got this geometry that's conserved over time. Also, all the molecules in here are rattling around over time. That's basically independent. Over short time spans, you'll have some dependence, but like any significant amount of time, You can have independence subject to this deterministic constraint of geometry of the market. So that again is a place where we expect to see some sort of ontological stability across different agents. This is not yet, this is like clearly not the whole story. In particular, like fleshing this full theory out, we should have a good idea of what basically all of the higher level structures are that like are convergent across agents. So for instance, I'm just like speaking some words at you right now. You guys know what I mean when I say these words for the most part. So probably each of these words being attached to some sort of latent structure in both of our heads that's convergent across both of our models, right? Because otherwise we wouldn't have a match here. Those structures like typically are not literally just a constraint, like some deterministic constraint between some stuff in the world that's far, right? Usually there's some higher level structure to it going on. Like with this marker, we said, you know, there's this thing conserved over space. There's also this thing conserved over time. These two interact in some way that's special for body objects. So there's these like higher level structures that we build out of these low level ontologically stable buildings. And core question in this chunk of the theory is what are those higher level structures? That's something we don't have most of the answer. Make sense?
How large or complicated do you expect the answer to that question to be? Like I'm thinking about the SICK project or something like that, which is of course way too big and unwieldy and like unmanaged.
So there's a lot of reason to expect that the answer can be expressed pretty small. Trying to decide whether I want to go into that. Okay, I'm not going to go into that in super detail right now, but I think key parts of the answer are like there should be a relatively small number of different atomic types of the thing, and then there's a whole lot of like building stuff out of those pieces, and there's like standard patterns, right? Let's get.
And is that ultimately physics and chemistry aren't that complicated or something else?
No, his language isn't that complicated.
Okay.
Actually, yeah. All right, representation. This category here, I think, is the one we currently understand best. Certainly the one where I have the most uncertainty about what the rest of the theory looks like. So I'm going to vibe a bit at what my best guesses are for like what goes into this. We certainly do not have theorems. We have very few conjectures, even wide open space. That said, some guesses. First, insofar as you want to like import stuff from thermodynamics or StatMech, this is where I think it's going to punch real hard. I'm not certain of that, but like if it's going to be relevant somewhere, it's going to be relevant right here. The intuition there is something about like adaptive systems equilibrating with structure in their environment and sort of representing that structure internally. Again, I'm vibing. Don't read too much. Another important aspect of what's going on here is, in a minute, we're going to talk about coherence. Coherence implies something about structure being sort of spread over a whole system in a way that like everything is sort of jointly optimal as opposed to little bits looking like they're optimized for very different things, but just happen to play together well. That's also a thing we'd expect to see in terms of representation. It doesn't necessarily mean that like the representation is spread over everywhere, but it means that we sort of have to look at the whole system at once. Like if you carve out a little part of a neural network, you can say things mechanistically about what that little part of a neural network is doing, but you're probably not going to be able to say the core things you want about what it's representing. You kind of have to look at the entire neural net in order to talk about representation. Another like way of framing things that come to a similar conclusion, if you think about a causal model with like a bunch of latent variables in it, we're picturing here, insofar as that latent structure is pretty deep, if you look at one of those latent variables and you're like, well, what does this latent variable mean? What does this latent variable represent? It doesn't even make sense to talk about that in isolation. Like a latent variable in a probabilistic model is entirely defined in terms of like what it says about your observables or what it says about other latency. So again, it doesn't really make sense to talk about what things represent if you just sort of carve them off in isolation. Talk about functionally what they do, but representation, you kind of have to like work with the whole system. Sadly, I don't have much more than that for answers at the moment, but hopefully that vibing was useful.
Question?
Yes.
Do you find any of the geometry stuff that's showing up from either SLT or computational mechanics relevant to
You're
you?
right. I should have brought that up. This is also the place where SLT would definitely fit. In particular, if you're thinking about either like SLT in SLT terms or SLT in compressibility terms, compressibility is like definitely our starting point for figuring out how representation is going to end up embedded in a system.
But I mean, going further, do you have an opinion on whether SLT is relevant or just it would be here?
I mean, it's absolutely the right sort of foundational. It doesn't directly ask or answer the core questions, but it's like a necessary thing that you're probably going to have to build it up. Yes.
I'm confused about what the question is here. More like you're saying, representation exists, and the question is, how do we tell where they exist? How did they come to exist?
So the questions I'd be asking here are things like, assume that this system is representing things internally. How do I go like poke at its internals and like back out its representation or like back out the representation of its representation? What can I read off from its internals?
How do I build observations to figure out what it's actually?
Exactly. And then other half of this would be like under what condition, like what conditions give rise. That's where something
Historically,
like
how
that.
did this arise?
Or not so much how it arises, so much as like, in order to understand how things typically end up embedded, like to get a general theory of how things end up embedded, we probably need to like be making some assumptions about the process that produced this thing or its own architecture, and like say something about it. Yeah. Yes.
I will pretend that I'm channeling Inman Harvey for a second. He is, at least it used to be, a strict anti-representationalist.
Cool.
And we know from things like Breitbart vehicles that representations are not necessarily needed to make something look like an agent.
Yeah, sure.
You look at Breitbart vehicles. Now, personally, I have an opinion about representations, why they're needed, but I feel that making representations slightly primal is maybe a bit too strong. What's your opinion about that?
So I think my main take here, there are places in here where we are talking about things being strictly necessary. So like, for instance, natural latents or condensation, if such and such conditions occur, then like stuff necessarily follows. My guess is that the core of this theory is not going to make statements about like full-blown logical implication. My guess is the core of this theory is going to be statistics. So as far as talking about representations and embedding, my guess is that what the sorts of theorems we ultimately want are going to say is, if you have a system that satisfies some very weak assumptions on its structure, like has sort of not too dense causal structure to it, you're putting selection pressure on this thing in some sort of environment, then in the statistically typical case, with exponentially high probability, it's going to end up internally factoring things in a way that mirrors natural abstractions in the environment. That is not a statement of logical necessity. Like, I would definitely you definitely expect that there are going to be at least some systems that don't factor internally in that way. Make sense? I'm going to not take that question right now because I want to get through all of this before we run out of time. Okay. Theorems on these. So the main piece that like I can gesture at right now and say we have a rough idea of how this works is at the basic agent level. In particular, we have this what we call our toy coherence theorem, which says you're in an MDP. So basically, you've got state at each time. It's 1, it's 2, dot. You've got your quote unquote agent, your basic agent, taking actions at each time that influence the state transitions. And we're imagining this thing trying to accomplish some goal that's just defined over the final state. Then we can ask the question, are there policies, things this agent could be doing at each time? Are there policies which are not optimal for any utility function over this final state? And the answer is yes, roughly, assuming non-triviality. Because if you have uniform utilities over the final state, then technically everything's. But there are policies which are not optimal for any non-trivial utility. Why is that important? That's important because it says that this concept of like being optimal for some utility function over final state is non-trivial, right? Like standard criticism of lots of notions of agency is, well, you've just defined things so a rock is an agent, right? Like if you say something is just a utility maximizer over universe histories, great, rock is an agent, boring. In this sense, rock, not an agent. So we get a nice non-trivial notion of agency here. And particular aspects I want to emphasize here is our restriction on utility over states at a later time. Insofar as this generalizes, thing I expect to generalize to is utility or goals or whatever, defined sort of sparsely, right? Like the key thing is you don't have a goal that's giving you credit for everything you're doing along the way. You don't have a goal that's like giving you credit for every little piece of the universe. Insofar as you have goals that are defined over like sparsely over the universe, maybe they're over stuff far away or in the future, that's where coherence starts to hit. And in particular, in this case, the condition that this policy is optimal for at least some utility function basically boils down to it doesn't have conflicting preferences. So if it chooses A over B, it will not choose B over A under some other circumstances. So it's like straight up your classic consistent preferences thing gives this notion. Yes, Lucius.
So technically, right, we happen to live in a universe where a given final state is consistent only with one single history.
Mm-hmm.
So if we're sort of imagining our agents like actually having preferences over the actual micro-level state of the world, then this theorem would kind of say nothing. So I guess it's sort of
we're going to get that's a great point. Just going to get to that. We're talking about general purpose agency. Okay, so that's coherence for basic agents. Once we get to general purpose agency, these agents can achieve multiple possible goals. Not taking that question right now. These agents can have multiple possible goals, and a key question becomes goals over what? We can also think of this in the case with subagents, insofar as I'm trying to outsource something to another subagent. I want to give that subagent a goal. Goals over what? And in the subagent's case, it clearly has to be something we can communicate, right? We talked about this. You sort of have to communicate your goal by expressing it in terms of divergent latents or something like that. I expect this generalizes to the sorts of goals that general purpose agents are going to pursue. Your utility, insofar as it makes sense to talk about a human's utility function, or your goals, insofar as it makes sense to talk about humans having goals, the things you have goals about, or the things you have goals over, are typically going to be these like higher level things like markers, as opposed to low level molecule states, right? I have goals about this marker. I would love for it to not be dead. I would love for it to draw when I take the cap off and rub it on the board. I don't particularly give a shit about the low level molecule states of this marker. This I expect to generalize for general purpose agents. Does that make sense? Okay. This also implies something about factorization of goals, like the sort of factorization that high-level agents like us do when we're factoring problems in them. It implies that when we factor these problems, we're going to be factoring it in a way that sort of mirrors the low-level structure we talked about over here, and the representations we already have in our heads matching that. Make sense? So the expectation here is that, this topic is going to be inherited to here. We're going to have these sort of natural convergent structures in the environment that get represented in our heads, and then our goals are defined over those. And then in the last step, we have like sub-agents or external agents that we're trying to outsource to, and we can then communicate those goals to those agents. And that, now that we're in the last like 3 minutes here, is sort of how this all flows together, right? The core thing is about you've got an agent or a super agent or a system of agents that's trying to achieve a goal in a fairly general purpose way. And it needs to structure its internal cognition, its internal planning or its internal factoring of the problem. How is it going to do that? Well, it's going to do that in a way that ultimately like grounds out in what sorts of abstraction are natural. And that's the topic. David, you help me move this whiteboard out of the way? Yep. Move back. Yeah.
I didn't know that you were John. I always knew you were the ball guy.
That's ball guy. Ball guy.
Oh, yeah. Right. And I think